Tonight we're going to talk about the end of everything. Not in a dramatic Hollywood way, in a calm, specific, factual way. We're going to walk through the scenarios that could, under the right conditions, end all life on this planet. Not just human life, all of it. And we're going to look at how some of those scenarios would unfold in a matter of hours. Here's the thing most people don't realize about extinction. When most people imagine the end of all life on Earth, they picture something slow. A gradual warming, a rising sea, a spreading drought, or they picture something dramatic but survivable. A war, a plague, something that kills most of us but leaves a remnant, a seed bank, a handful of survivors. Life finds a way, as the saying goes. But the saying isn't always true. There are specific physical events, some of them documented, some of them theoretically possible within the known laws of physics, that would not leave a remnant, that would not allow life to find a way. Events so total and so fast that the question isn't who survives. The question is how long the process takes. And in some of these scenarios, the answer is measured in hours. Sometimes less. By the end of tonight, you're going to understand what those scenarios actually are, what the physics behind them looks like, what the specific sequence of events would be, and why the line between a civilization-ending event and a planet sterilizing one is thinner than almost anyone thinks. This isn't a horror story. It's physics. And physics, when you look at it clearly and carefully, is more clarifying than frightening. Let's start with the most commonly discussed threat. The one that gets the most attention. The one that actually did it before. An asteroid. Most people know the story in broad strokes. About 66 million years ago, a rock from space hit the Earth, and the dinosaurs went extinct. That's the version we all learned. But the details of what actually happened that day, and in the hours and weeks that followed, are specific enough that they change the picture completely. The object was somewhere between 10 and 15 kilometers in diameter. Put that in physical terms. Mount Everest is about 8.8 kilometers tall. The asteroid that hit Earth was taller than the highest point on our planet, measured as a sphere flying through space. And it was travelling at roughly 20 kilometers per second. That's 72 kilometers per hour. A commercial jet flies at about 900 kilometers per hour. The asteroid was moving 80 times faster than a cruising aircraft. At that speed, it would travel from Los Angeles to New York City in about 5 seconds. When something that large and that fast hits the atmosphere, it doesn't slow down the way a smaller object does. It punches through the atmosphere as if it isn't there. The air beneath it compresses so violently that it heats to temperatures exceeding 50,000 Kelvin. That's roughly 9 times hotter than the surface of the Sun. The ground and the asteroid itself vaporize simultaneously. In the first second of impact, everything within a radius of several hundred kilometers is simply removed. Not destroyed. Removed, vaporized into plasma. The crater left at Chicxulub on the Yucatan Peninsula in Mexico is about 180 kilometers across. To walk around its circumference at a brisk pace, you'd need roughly 3.5 weeks of continuous walking, and that's the hole left in solid rock. The explosion itself was equivalent to roughly 100 teratons of TNT. That's 100 trillion tons of explosive force. The largest nuclear weapon ever detonated, the Soviet Tsar bomber, tested in 1961, released about 50 megatons of force. The Chicxulub impact was about 2 million times more powerful than the Tsar bomber. 2 million in the first 2 hours after the Chicxulub impact. Here's what happened. The ejector, the vaporized rock blasted upward by the explosion, shot into the upper atmosphere and into space, then fell back down globally. Those tiny particles of rock, re-entering the atmosphere at high speed, heated the air as they decelerated. The global temperature of the lower atmosphere spiked for a period of perhaps an hour or 2. The surface of the Earth was as hot as the inside of an oven. not just near the impact site. Globally, anything exposed at the surface that could burn did. Forests ignited simultaneously across the northern hemisphere. Here's what most people don't realize. It wasn't the impact itself that killed the dinosaurs, it was what happened next. The impact winter. The soot from global wildfires combined with sulfur dioxide from vaporized rock blocked sunlight for months to years. Photosynthesis largely stopped. The food web collapsed from the bottom up. Most large animals that needed large amounts of food to survive couldn't make it. The dinosaurs didn't die in the explosion. They starved in the dark, or they froze. The process that killed most species took months to years, not minutes. But here's the critical distinction. The Chicxulub impact was large enough to cause a mass extinction. It killed roughly 75% of all species, but it didn't sterilize the planet. Life survived. Small animals, insects, plants with seeds buried in soil, microbes in every environment imaginable, bacteria kilometers underground. All of these survived. The Chicxulub impactor was big enough to reset the evolutionary clock, but not big enough to erase it entirely. What would it take to actually end all life? Not most life, all of it, including the bacteria living 3 kilometers underground in solid rock, including the heat-loving organisms at the bottom of the ocean around hydrothermal vents, including the spores of organisms that can survive complete desiccation and intense radiation. What would erase every one of those? The answer is something much, much larger, and the largest documented impact event in Earth's history gives us a rough benchmark. About 3.9 billion years ago, in a period called the Late Heavy Bombardment, the inner solar system was being pelted by a sustained barrage of very large objects. Some of the impacts during this period were large enough that the entire ocean may have been vaporized, not just heated, vaporized, turned to steam, and when the ocean evaporates, the steam acts as a greenhouse gas that traps the remaining heat, which prevents the ocean from condensing back for a very long time. Some researchers call this an ocean vaporizing impact, and the threshold to achieve it is an impactor somewhere around 500 kilometers in diameter. 500 kilometers in diameter. The largest asteroid in the solar system today is Ceres, which lives in the asteroid belt between Mars and Jupiter. Ceres is about 940 kilometers across, something 2/3 the size of Ceres hitting Earth at 20 kilometers per second. The energy released would be about 3 times 10 to the 30th joules. To put that in physical terms, the Sun radiates that much energy in about 8 minutes. In those 8 minutes, the Sun shines about 1 trillion times more brightly than all the light reaching Earth on a clear day. The Sun pours that energy out continuously. This impact would release it all at once, at one spot on the Earth's surface. Everything we know about the physics says that an impact of this size would end life completely. Not by blocking the Sun, by vaporizing the ocean and heating the entire solid crust to temperatures incompatible with any known life. The bacteria in the deep rock would be cooked. The organisms at the ocean floor would be boiled and then dried. The spores in the soil would be incinerated. The process would take days to fully play out. But within the first 2 hours after impact, the global temperature would have climbed to levels where no known organism could survive. Is this scenario possible today? Could something 500 kilometers across hit Earth? The short answer is no, not in any plausible near-term scenario. We've surveyed the solar system well enough to know that no object this large is on a collision course with Earth. The large objects in the solar system are in stable orbits. An orbit would have to be dramatically perturbed to send something this large toward us. The most realistic pathway would be a gravitational interaction with Jupiter or another large body, which can redirect smaller objects, but not easily redirect something as massive as what we're describing. This particular threat is well off the near-term risk table. but it's worth understanding that this exact thing happened to Earth once before. What we now call life survived the late heavy bombardment because the impacts, while catastrophic, were spaced out enough that life had time to recover between them. We exist because the timing was just survivable. A slightly different distribution of large objects in the early solar system, and there might have been no recovery window. Now, let's go somewhere completely different. Let's talk about something that comes not from below, but from above. From deep space. And that can end all life on a planet from a distance of thousands of light years, a gamma-ray burst. Gamma-ray bursts are the most energetic explosions in the universe. They occur when a massive star collapses into a neutron star or black hole, or when two neutron stars collide and merge. The energy released in a matter of seconds exceeds the total energy output of our Sun over its entire 10 billion year lifespan. The Sun will burn hydrogen for 10 billion years. A gamma-ray burst releases more energy than all of that, in somewhere between a fraction of a second and a few minutes. The energy is focused into two narrow jets, one from each pole of the collapsing star or merging objects. These jets travel at very close to the speed of light. The material in the jets moves at 99.9% of light speed, and the jets are narrow, typically covering only a few degrees of sky. So you have to be in the line of fire. If the jet points at you, you receive an enormous dose of gamma radiation. If it doesn't, you might see the burst as a flash in the sky, but survive it without consequence. If a gamma-ray burst occurred within about 6,000 to 8,000 light years of Earth, and the jet pointed directly at us, what would happen? 6,000 light years. If the Milky Way were a pizza 16 inches across, 6,000 light years would be about the thickness of a strand of hair measured from the edge. That's close in galactic terms. Our galaxy is 100,000 light years across. The gamma rays would hit Earth's atmosphere before we had any warning. Light travels at the same speed as gamma rays. The burst itself would arrive the moment we saw the flash, and there would be no warning from the dying star before it burst. The sequence is burst, arrival, simultaneous. We would have zero time to prepare. Here's what would happen in the first few minutes. The gamma radiation would strip electrons from molecules in the upper atmosphere. Those freed electrons would collide with nitrogen and oxygen molecules, producing a cascade of chemical reactions. The most important of these would be the massive production of nitrogen dioxide. Nitrogen dioxide is the chemical that makes urban air pollution, that orange-brown haze on a smoggy day. A gamma-ray burst would produce enough of it globally in minutes to turn the sky a deep brown colour that would be visible from the surface. But the nitrogen dioxide is a symptom, not the damage itself. The real damage is to the ozone layer. The reactions triggered by the gamma radiation destroy ozone on a global scale. The ozone layer, which sits in the stratosphere at an altitude of about 15 to 35 kilometers, absorbs ultraviolet radiation from the sun. Without it, the UV reaching the surface increases dramatically. On a planet like ours, that UV increase would be lethal to most surface life within weeks. Phytoplankton, the microscopic organisms in the ocean surface that produce about half of Earth's oxygen through photosynthesis, are extremely sensitive to UV radiation. A massive ozone depletion event would devastate phytoplankton populations globally. Since phytoplankton form the base of the ocean food web, their collapse would cascade upward through the food chain. Ocean fish, marine mammals, seabirds, all dependent on phytoplankton directly or indirectly. On land, the immediate UV increase would cause mass die-offs among organisms that cannot shield themselves from the radiation. Small organisms, those without thick skin, shells, or burrowing behaviour, would be hit hardest first. Insects, which are the foundation of terrestrial food webs, would suffer heavy losses. Without insects, the plants that depend on them for pollination fail. Without plants, the animals that eat plants starve. The cascade moves upward, but would a gamma-ray burst actually end all life? Probably not. For the same reason the Chicxulub impact didn't. Life underground and deep in the ocean would be relatively shielded. Bacteria in deep rock are completely untouched by surface UV. Extremophiles in hydrothermal vents are insulated by kilometers of ocean water. A gamma-ray burst would cause a catastrophic mass extinction, possibly one of the largest in Earth's history, but it would likely leave a biological base from which life could eventually recover. Some researchers have proposed that one of the major mass extinctions in Earth's past, the late Ordovician extinction about 443 million years ago, which killed about 85% of marine species, may have been caused partly by a gamma-ray burst. The evidence is indirect, but the pattern of extinction, which preferentially hit shallow water organisms and was associated with ozone depletion signatures, is consistent with what a gamma-ray burst would cause. Now, here's the key point about gamma-ray bursts and the current risk. The Milky Way produces roughly 1 to a few gamma-ray bursts per million years. That sounds infrequent, but the galaxy has been here for 10 billion years. In that time, there have been something like 10,000 to 100,000 gamma-ray bursts within the Milky Way alone. Most pointed the wrong way. Most occurred in parts of the galaxy too far away to matter. But statistically, across billions of years, some of them pointed at Earth. And Earth and life are still here. The filters we've passed before are real. But the question remains: what natural event delivered in a matter of hours could sterilize the planet completely? Not just cause a mass extinction, actually erase all life? Let's go deeper. Let's talk about a nearby supernova, not 6,000 light-years close, really close. A supernova at 25 to 30 light-years from Earth would be a civilization-ending event. At that distance, the burst of radiation would deliver a dose to Earth's surface far exceeding the lethal threshold for essentially any organism. The ozone layer wouldn't just be depleted, it would essentially cease to exist for an extended period. The UV flux at the surface would be roughly 100 times its current level. At that intensity, sunlight itself would be lethal. Not gradually, quickly, but a supernova close enough to actually sterilize the planet entirely, meaning close enough to kill even deep subsurface life through radiation penetrating kilometers of rock, would need to be within a few light years. Within a few light years of Earth, there are currently no stars massive enough to go supernova that close. The nearest massive star candidates are much farther away. Betelgeuse, the red supergiant at Orion's shoulder that people discuss as a supernova candidate, is about 700 light-years from Earth. Close enough to put on an extraordinary light show, not close enough to harm us at the surface. At 700 light-years, even a supernova 10 times more powerful than average would produce UVA levels that the ozone layer could survive with some damage. But let's not stay stuck on what's likely. Let's think about what's physically possible, even if rare. Because understanding the upper bound of what the universe can do to a living planet is part of the picture. There's another category of object that a supernova can leave behind: magnetars. A magnetar is a neutron star with an extraordinarily powerful magnetic field. A neutron star is the collapsed core of a massive star, roughly the size of a city, but containing more mass than our Sun. A teaspoon of neutron star material would weigh about 900 million tons, about the same as 150 Great Pyramids of Giza in a teaspoon. A magnetar has a magnetic field about 1 trillion times stronger than Earth's. Earth's magnetic field deflects solar wind particles and moves compass needles. A magnetar's field is so intense that it would distort the electron orbitals of atoms. The chemistry of matter changes in the presence of a field that's strong. If a magnetar were placed where the Moon is, about 384,000 kilometers from Earth, the magnetic field would pull the iron out of your blood from that distance. You wouldn't need to be near it. The field would reach you here from the Moon's distance. Magnetars occasionally undergo what's called a starquake, a sudden rearrangement of the crust of the neutron star caused by the buildup of magnetic stress. In 2004, a magnetar called SGR 1806-20, located about 50,000 light-years away, underwent a giant flare. 50,000 light-years is on the other side of the Milky Way. That single flare released more energy in 0.2 of a second than our Sun releases in 250,000 years. In 1/5 of a second, the pulse was so intense that it briefly ionized Earth's upper atmosphere, measurably affecting the ionosphere from 50,000 light-years away. If that magnetar were 10 light-years from Earth rather than 50,000, the flare would have stripped away a substantial portion of the atmosphere. At 1 light-year, it would have been catastrophic. But magnetars are formed in supernovae, and the massive stars required don't currently exist close to Earth. Again, we're looking at real physical phenomena that genuinely threaten planets, just not currently pointed at us, and not currently in our neighbourhood. Let's go to something more immediate. Something that could happen without any astronomical precursor. Something that could start in a laboratory, an engineered pathogen. Most people think of biological warfare in terms of things we already know. Anthrax, smallpox, plague. These are real threats, and they're dangerous. But they're not planet sterilizing. The reason is that pathogens that kill their hosts very quickly and very efficiently tend to burn out. They run out of hosts before they can spread globally. Ebola is devastating but self-limiting for this reason. Its kill rate is so high and it spreads so fast that it collapses its own outbreak before it can travel far. But here's what's changed in the last 30 years. Biotechnology. The tools that allow us to read and write DNA are advancing in capability and falling in cost at a rate that mirrors the trajectory of computing. CRISPR, the gene editing tool that allows precise modification of DNA sequences, was first demonstrated in human cells in 2012. The equipment required to use it now fits on a benchtop. It costs a small fraction of what comparable gene editing cost in the 1990s. A researcher with moderate training can use it. The threshold of technical expertise required to make meaningful modifications to a pathogen has been dropping steadily. A hypothetical engineered pandemic pathogen designed specifically to maximize transmission, while avoiding immune recognition, could in principle be given the transmissibility of measles, which is one of the most contagious pathogens we know, combined with a very long pre-symptomatic infectious period. The kind of incubation time that allows a person to infect dozens of others before knowing they're sick. Combined with near-total lethality, measles without a vaccine has a basic reproduction number of between 12 and 18. That means one infected person in a fully susceptible population infects on average 12 to 18 others. Each of those infects 12 to 18 more. The math of exponential growth is brutally fast, but even a pathogen designed this way would not end all life on Earth. Bacteria would survive. Most insects would survive. Most plant life would survive. What an engineered pandemic could credibly end is human civilization, and potentially all large mammal life. But the biosphere would continue. Life on Earth would not end. Something like the conditions after the Permian extinction, where the dominant life forms were killed off, would emerge. A world of microbes, insects, fish, and eventually, over tens of millions of years, new complex life evolving from the survivors. To end all life with a biological agent, you would need something that could reach and kill organisms in environments that no pathogen currently reaches. Bacteria kilometers underground. Organisms in superheated hydrothermal vents. Spores in dry rock. No pathogen evolved on the Earth's surface can do that. Biology as a weapon of total sterilization hits a wall. Life is too diverse, too distributed, too hardy at its edges. But what about something that acts on the physical environment itself, rather than on individual organisms? What if the agent of extinction wasn't biological? What if it was chemical? Let's talk about runaway greenhouse warming, not the gradual warming we're experiencing now. The runaway version, the kind that happened on Venus. Venus is currently 465 degrees Celsius at the surface. Hot enough to melt lead. Hot enough that any organism we know of would be instantly destroyed. Venus likely had liquid water on its surface billions of years ago. Some models suggest it was habitable for as long as 2 billion years. Then something pushed the climate over a threshold. The greenhouse effect became self-reinforcing. More heat meant more water evaporation. More water vapor meant stronger greenhouse effect. The ocean evaporated, the temperature climbed. The atmosphere we see today is the result. The trigger for Venus's runaway greenhouse was probably an increase in solar output as the Sun aged, combined with Venus's slightly closer distance to the Sun. Venus sits about 38 million kilometers closer to the Sun than Earth does at the distance of Venus's orbit. Earth would also likely undergo a runaway greenhouse. It's not just about the composition of the atmosphere. It's about being close enough to the energy source that the feedback can't be stopped once it starts. Could we trigger a runaway greenhouse on Earth with industrial emissions? The current scientific consensus is no. Not with any realistic level of fossil fuel burning. We could warm the planet dramatically, and we are doing that. But the amount of carbon available in accessible fossil fuel reserves, burned completely, would not push Earth over the threshold into Venus-style runaway. The feedbacks would be severe. The damage would be enormous. But life would survive. Even complex life would survive, though profoundly changed. But there is a theoretical threshold, a level of warming that, if reached by any means, would begin the feedback. It requires the ocean to begin evaporating faster than it can condense. For Earth, that threshold is thought to require surface temperatures of around 70 to 80 degrees Celsius, maintained globally for long enough to get the process started. Today, we're at a global average of about 15 degrees. The gap between where we are and where the runaway begins is substantial. But it's not infinite. If something drove the global temperature up by 60 degrees Celsius, rapidly, a very large impact, a nearby supernova that destroyed the ozone layer and let UV heating begin, a dramatic change in solar output, the runaway process could start, and once started, it wouldn't stop. On a timescale of maybe 1 million years, Earth would become Venus. And on Venus today, the deepest rocks are at 465 degrees Celsius. Even the most heat-tolerant microbes on Earth, the ones that live at the edges of boiling springs, die above about 130 degrees. At 465 degrees for millions of years, every crevice in the rock, every trace of water, every possible hiding place for biology would be sterilized. Runaway greenhouse is the slow version of total sterilization. It takes 1 million years or more, not 2 hours. But the starting event, the thing that triggers it, could happen in 2 hours, and once triggered, there's no stopping it. Now, let's go to something that operates on a completely different timescale. Something that doesn't give life 1 million years to adapt. Something that would be over before most organisms could respond at all. Let's talk about vacuum decay. This is the most exotic item on our list, and it's the one that is simultaneously the most theoretically serious and the most impossible to prepare for. In quantum field theory, the vacuum, meaning empty space itself, has an energy state, the energy of nothing. And in our current universe, physicists believe the vacuum might be in what's called a metastable state, not the lowest possible energy state. A local minimum, like a ball resting in a bowl partway up a hill. The ball is stable in the sense that small disturbances don't knock it out of the bowl. But if something gave it enough energy, it could hop over the edge of the bowl and roll all the way down to a lower state. In this analogy, the bowl is our current universe, and the lower state, the one at the bottom of the hill, is a completely different configuration of the laws of physics. In this lower state, the fundamental constants of nature would all be different. The mass of the electron, the strength of the electromagnetic force, the character of the weak nuclear force. Not slightly different, completely different, in ways that would make chemistry as we know it impossible. The atoms that make up matter wouldn't hold together in the same way. Nuclei would have different binding energies. Molecules as we know them simply wouldn't form. If vacuum decay were triggered somewhere in the universe, a bubble of the new, lower energy vacuum would form at that point. The surface of the bubble would expand outward at the speed of light, exactly the speed of light. Not slower, not faster, and inside the bubble, the laws of physics would be different. Everything the bubble passed through would be instantly converted to whatever matter can exist in the new state, which is likely very little, if anything. The bubble would be completely undetectable until it arrived. Because it travels at the speed of light, there's no signal, no warning, no precursor wave that could outrun it. The moment you could observe it coming is the moment it arrives. And, in the moment it arrives, every atom in your body is reorganized according to a different set of physical laws. There's no experience of it, no sensation. The process is faster than any biological or physical signal could propagate through matter. You'd be converted before the neurons carrying any sensory information could fire. An entire planet, an entire galaxy, an entire observable universe could be converted by a vacuum decay bubble in the time it takes light to cross it. The observable universe is about 93 billion light-years in diameter. A vacuum decay bubble travelling at light speed would take 93 billion years to cross it, but every point along the way would encounter the bubble with zero warning, and at every point the conversion would be instantaneous. Here's the uncomfortable part. We don't know if this can happen. We don't know if our vacuum is metastable. The Higgs boson discovered at CERN in 2012 has a mass that puts the vacuum stability of our universe in an ambiguous zone. Some calculations suggest the vacuum is stable, others suggest it's metastable. The uncertainty in the Higgs mass and other fundamental parameters means we can't be confident either way. The most careful analyses suggest our vacuum is probably metastable, but the rate of decay, if any, would be astronomically slow under normal conditions. The probability of spontaneous vacuum decay in any given region of space in the age of the universe might be essentially zero. But the key phrase there is spontaneous, high-energy physics events like the collision of extremely energetic cosmic rays with atomic nuclei in the upper atmosphere happen constantly. And particle accelerators like the Large Hadron Collider create extremely high-energy collisions. Critics of particle accelerators have occasionally raised the concern that a sufficiently high-energy collision could seed a vacuum decay event. Physicists have carefully analysed this and concluded that it's not a concern for the energies we can achieve. The LHC's most energetic collisions are far below the energy at which vacuum decay could be seeded, and cosmic ray collisions, at energies far exceeding anything we can produce, happen naturally all the time without apparent consequence. But in principle, if something triggered vacuum decay, if a sufficiently energetic event somewhere in the universe had already triggered it billions of years ago, a bubble of destroyed physics could be travelling through the galaxy right now, and we'd have no way of knowing until the moment it arrived, which is also the moment nothing remains. The planet, the solar system, the galaxy, encountered sequentially as the bubble expands at light speed, not simultaneously. But from the perspective of anything the bubble converts, the process is instantaneous. Vacuum decay is the ultimate extinction event. It doesn't just end life, It ends the physical substrate on which life was built. It ends chemistry. It ends atoms as we know them. It ends the laws of physics that allowed stars to form, and planets to orbit, and molecules to organize into cells. It is total in a way that an asteroid or a supernova simply isn't. And it cannot be detected, prepared for, or survived by anyone, anywhere. Let's come back from the most extreme scenario and work our way through some of the more immediate and specific ones. Because the scenarios in between the mundane and the cosmically extreme are where the most useful thinking lives. Let's talk about what would happen if Earth's magnetic field failed completely and suddenly. The magnetic field, generated by the convection of liquid iron in Earth's outer core, extends into space and forms what's called the magnetosphere. It deflects the charged particles of the solar wind. Without it, those particles would hit the upper atmosphere directly. Over millions of years, this solar wind erosion would gradually strip away the atmosphere. Mars lost most of its atmosphere this way, after its core cooled and its magnetic field weakened. But on a short timescale, the immediate loss of the magnetic field wouldn't end all life. It would dramatically increase radiation at the surface. It would make the aurora visible globally and constantly, not just near the poles. It would disrupt satellite communications, GPS, and power grids through increased exposure to solar energetic particles. It would increase the risk of radiation-induced cancer in exposed organisms. And it would do these things permanently or until the field regenerated. Over years to centuries, the gradual atmosphere loss would become significant. But on the time scale of hours, the end of the magnetic field would be disruptive, possibly catastrophic for technology-dependent civilization, but not a complete sterilization of life. The ocean, which provides physical shielding from radiation by virtue of having miles of water above deep-sea organisms, would remain habitable. Organisms in deep soil or rock would be largely unaffected. Even surface organisms would have some radiation protection from the atmosphere itself, which shields against many types of solar particles, even without the magnetic field. Here's something that might surprise you though. We've discussed how a magnetic reversal involves the field weakening dramatically before it flips. During that weakening, the protection against solar particles decreases substantially, and Earth has experienced hundreds of reversals. Life has survived every one. The field isn't binary. It doesn't switch off and then on. It weakens over thousands of years, reorganizes, and strengthens again. Life in all its distributed hardness rides out those transitions. Let's now talk about something that combines several threats. The scenario where the Sun behaves unusually. The Sun is a relatively stable star. Compared to many other stars, it's quiet. It doesn't flare dramatically or erratically, but it does produce what are called coronal mass ejections. Large bursts of magnetized plasma ejected from the corona and sent streaming through space. Most of these miss or produce moderate effects. Some produce significant ones. The Carrington event of 1859 was the largest solar storm in recorded history. A coronal mass ejection hit Earth's magnetic field with enough force to produce auroras visible as far south as Cuba, and produced currents in telegraph lines strong enough to shock telegraph operators and set telegraph paper on fire. The global telegraph infrastructure, the internet of its day, was temporarily fried. That was in 1859, with a minimal electrical infrastructure. In our current world, with electrical infrastructure everywhere, satellites providing GPS and communications, power grids spanning continents, and essentially every critical system depending on electronics, a Carrington-level event would be transformative. Some estimates put the damage from a Carrington equivalent event today at between $1 and $2 trillion in the first year alone, with recovery taking years to decades. Power outages in the most affected regions could last months. Without power, Water treatment fails, food distribution fails, hospitals lose critical systems. The human cost could be severe, but would it end all life? No. Not even close. A Carrington-level event would be a civilizational catastrophe. It would not be an extinction event. Even the most vulnerable organisms, though sensitive to electromagnetic disruption, would mostly be unaffected because biology isn't as dependent on electrical infrastructure as human civilization is. Birds navigate by magnetic fields, and a severe solar storm disrupts their navigation. But it doesn't kill them. The solar event that would actually threaten life would need to be qualitatively different from a coronal mass ejection. And the Sun, being the specific kind of star it is, a relatively stable G-type main sequence star, isn't likely to produce that kind of event on any human timescale. Red dwarf stars, those smaller, cooler, dimmer stars that make up the majority of stars in the galaxy, are much more prone to violent flaring. A planet around a red dwarf faces a very different solar environment than Earth does, which is one of the reasons the habitability of red dwarf planets is actively debated. In 2012, a solar storm that would have been far more powerful than the Carrington event erupted from the Sun. The coronal mass ejection was directed away from Earth. If it had been pointed at us, it would have been approximately 10 times more powerful than the Carrington event. Some analyses suggest it might have been strong enough to cause multi-year power grid failures across entire continents. But even that wouldn't end all life. The atmosphere absorbs X-rays and gamma rays before they reach the surface. A dramatic flare would damage the ozone layer, much like the gamma ray burst scenario, but to a lesser degree, causing increased UV at the surface for months to years, mass die-offs of UV-sensitive organisms, disruption of food webs, but not sterilization.